The essential process of drawing a schematic that has an electrical behavior that approximates to that of a real system is called modeling. It is models that allow us to analyze the products that we use in our day-to-day life. Suppose you have a flashlight and you want to redesign it to consume less power. Drawing the flashlight on a sheet of paper will not be of any help, even if your artistic abilities are better than ours, which is very likely. Modeling each component of the flashlight will give us a circuit schematic that we can analyze and improve. There are 4 components on a simple flashlight: 2 batteries, a light bulb, a switch, and pieces of metal that connect all of the components together. We've already modeled the battery as an ideal voltage source and the light bulb as a resistor. We also looked at switches and how they are used to open and close circuit loops. If you look inside a flashlight, you'll probably see 2 batteries connected in series, with the positive terminal of one touching the negative terminal of the other. Let's draw 2 voltage sources in series to model this part of the system. Next, you'll see that the positive terminal of the second battery is touching a piece of metal. If you look on the other side, the light bulb is also touching this piece of metal. Since metals are conductors and the 2 components are touching the same conductor, we know that the battery and the light bulb are electrically connected. We draw a wire to show this connection. On the negative side of the first battery, you'll find a metal spring. The purpose of this spring is twofold. It keeps the 2 batteries in place and also creates an electrical connection between the negative side of the battery and another piece of metal. This second piece of metal runs from the spring to one side of the switch. We show this metal connection by drawing a wire from the battery to the switch. Since the spring is also metal, it becomes part of the wire in our model. Finally, we know that when the switch closes, a loop must be created for electrons to flow, so the other side of the switch must connect to the remaining terminal of the resistor. There it is, a circuit schematic that we can analyze. We know the value of the sources by looking at the rating of the batteries. The only unknown parameter is the resistance of the light bulb. We can use an ammeter to measure the current and then apply Ohm's law to find the resistance. Let's suppose we have 2 1.5 volt batteries. We close the switch and we measure a current of 0.5 amps. What is the resistance of the light bulb? Ohm's law tells us that voltage is current times resistance. Since we have 2 1.5 volt batteries in series, the voltage across the resistor is 3 volts. The current was measured to be 0.5 amps. Then dividing 3 volts by 0.5 amps gives us a resistance of 6 ohms for the light bulb. If we want to reduce the power consumption of the flashlight, we need to reduce the current drawn by the bulb. How can we do this? We can accomplish a lower current by increasing the resistance of the filament. More complex systems can also be modeled and optimized following the steps we performed here. An interesting model is that of a human body. We know that humans are conductors, so electricity can flow through us. Looking at the resistance of each part of our bodies, we can do a simple model of ourselves. For instance, the average resistance of our arms and legs is 500 ohms, and our torso is in the 100 ohm range. We can draw this with resistors following the shape of a body. If we connect a voltage source between one arm and one leg, then we form a closed loop where current can flow. It is the current flowing through our hearts that can be fatal. Touching the metal connection of a wall plug creates exactly this scenario. You may be wondering how a closed loop is formed when touching a plug. It is clear that the hand is connected to one side of the source, but where is the second connection? The foot isn't touching the plug. This is where the concept of ground comes into place. We know that voltage must always be specified with respect to a reference. In every circuit, there is always a universal reference. What we mean by universal is that all voltages in the system are referenced to this single point. This is similar to sea level and height. Sea level is used as a reference to specify the height of a city or a mountain. For instance, Mount McKinley in Alaska is 20,236 feet above sea level. You may wonder why we use sea level as a reference for height. Since the ocean is so big, it is very hard for its own level to change drastically. For instance, if we have a rainy day, the level of the ocean will not be affected. Therefore, the sea level is fairly constant in time and thus a good reference. Just like most places are above sea level, typically the point of lowest energy in a circuit is used as the reference, so that all voltages are above the reference. Here's our word of the day. The universal reference in a circuit is called a ground, and it's abbreviated to GND. The symbol shown here is used in schematics to show the location of the ground. From now on, we'll always show a ground in our circuits. Once a ground is specified, voltages are implicitly referenced to this point. Your house, like any other electric network, has a reference ground. Can you guess what this reference point is? The reference for all houses is Earth. There is a metal connection between each house and the Earth. When you touch a plug, your hand is connected to a source and your foot is touching the floor. This floor is in contact with the Earth. Since Earth is the ground of the main line of energy in your house, you're closing the circuit and allowing current to flow. Wearing shoes helps prevent electrocution by insulating your feet from the ground. Earth is used as a ground for the same reason the sea is used to measure height. The vast size of the Earth ensures that its voltage is fairly constant regardless of the amount of electricity that flows through it, from our appliances and even from intense thunderstorm lightning.